For decades, defending a network meant writing rules. Security analysts manually built lists of bad IP addresses and known virus signatures, essentially creating digital wanted posters to block threats at the door. But today, malicious software can mutate by the second. An attacker can automatically generate thousands of unique variations of a single payload, easily slipping past rigid scanning mechanisms and completely overwhelming human defenders. To counter this, security operations centers adopted the ML-IDS, or Machine Learning Intrusion Detection System. Instead of searching for a fixed list of known threats, these systems review millions of network interactions to learn the statistical baseline of normal, everyday traffic. Once the algorithm understands what a healthy network looks like, it simply flags anything that deviates from that pattern. Relying on statistical models to govern security introduces a distinct vulnerability known as adversarial machine learning. If an algorithm is the sole judge of what enters a network, an attacker's job changes. They no longer have to force their way through a firewall. They just have to figure out the exact mathematical criteria the algorithm uses and present data that satisfies it. This tactic is called an evasion attack. It is a precise process where an attacker carefully modifies a genuine, damaging payload so that its measurable characteristics align with what the defending model considers safe. Standard-setting agencies like NIST are actively mapping this terrain. Historically, these institutions cataloged software bugs and open ports, but the focus is expanding to address how mathematical models themselves can be manipulated. The MIT organization has even developed a dedicated framework called Atlas, providing a shared playbook for analysts to track how machine learning blind spots are actively exploited in the wild. Network defense is now a continuous process of testing and anticipating the logic of the algorithm standing guard. A clear example of how these defense systems are engineered is CyberFlow IDS, a real-world Capstone project developed by Dr. Raul Gacusan at the Asian Institute of Management. To find the most effective algorithm, CyberFlow used a tournament approach. 4 different machine learning models were trained and evaluated against a dataset of over 126,000 labeled network flows. This chart shows the naive Bayes model's performance. Its recall hit nearly 98%, successfully detecting almost every actual attack. But its precision was only 31.8%. More than 2/3 of the traffic flagged as malicious was actually safe. In a live security operations center, a model like this would generate hundreds of false alarms every hour, eventually causing human analysts to ignore the alerts entirely. The project ultimately deployed the random forest model, which offered a much more balanced ratio of speed, precision, and accuracy. In applied data science, deploying a slightly lower accuracy model that produces reliable, actionable alerts is highly preferable to a theoretically perfect model that paralyzes the team with noise. Once a balanced model is live, attackers begin looking for ways to bypass it. One method is a poisoning attack. If an attacker can infiltrate the training data before the system goes live, they can teach the AI that their specific backdoor behavior is part of the normal baseline. But for a system already in production, they rely on evasion. As outlined in the project's laboratory exercises, attacking the deployed model requires altering the shape of the incoming traffic. The attacker keeps the underlying malicious payload intact, but changes how it travels. Instead of sending an aggressive burst of data that triggers an alert, they spread the transmission out over a longer period of time. This visualization shows the feature weights the AI measures, like packet size and frequency. Attackers calculate these thresholds, formatting traffic to stay within normal limits. By subtly modifying packet spaces and sizes, the malicious traffic slips into the green zone, completely evading detection. Because machine learning relies on statistical boundaries, every model has mathematical blind spots that can be identified and systematically exploited. Knowing these blind spots exist means security teams cannot deploy an algorithm and simply walk away. Instead, they use a technique called adversarial training. Defenders deliberately attack their own systems using the exact evasion tactics attackers employ, forcing the model to learn and recognize the disguised behavior. They also deploy ensemble defenses, running multiple machine learning models at the same time. Since different algorithms weigh features differently, An input that fools one node is likely to be caught by another. Over time, teams perform drift monitoring, continuously auditing the system's decisions against live traffic to detect if its accuracy is quietly degrading. The modern defensive posture requires a daily cycle of testing, breaking, and retraining the algorithms that guard the network. The engineering focus has moved beyond finding flaws in application code. Securing a system now requires defending the underlying logic of the artificial intelligence itself. This requires connecting academic data science with practical threat mitigation, a focus central to initiatives like the Digital Workplace Readiness Program. When artificial intelligence fights artificial intelligence, the winner is determined by who has the deepest understanding of the machine's mathematical boundaries. The structural concepts and laboratory testing for this digital battlefield were established by Dr. Raul C. Gacusan in his real-world CyberFlow IDS Capstone